Hi there. So today I wanted to talk to you about the absorption and emission spectra, specifically of hydrogen. But first, I'm going to start off with sort of a general introduction into what is an emission spectrum. You get a discrete line spectrum when you have a low pressure gas and you subject it to a voltage. And that's shown here in this common physics demo, where you've got some rarefied gas inside of a tube and you hook it up and apply a voltage in between either end, and this excites the gas, okay? Another way to do this is to heat the gas through some other means. Pyrolysis is a common spectroscopy technique where you basically set things on fire and looking at the light that comes out of the fire. So that's another idea. Now, observation and analysis of these spectral lines is called emission spectroscopy. The simplest line spectrum is that for atomic hydrogen. And at the time that this was studied in the late 1800s, they understood that the spectrum from the gas acted like a fingerprint for the gas. And it was known that any successful model of the atom had to also explain these spectra. Now, other atoms exhibit completely different line spectra. It's unique, it's a fingerprint. In this image you see the line spectra for hydrogen, mercury, and neon, for example, and you can see that none of these is the same. And it's that way for any other gas that you look at too. Now, because no two elements have the same line spectrum, it's a practical and sensitive technique for identifying the elements present in unknown samples. And this is often done in fields like chemistry, for example, when they want to know what the composition of an unknown sample is. So you know what the spectra of the elements are. That's all known now. So if you analyze an unknown sample, then you can compare that to the reference spectra that you have for the elements and figure out what's in your gas. You can also look at an absorption spectrum, and that's obtained when you pass white light from a continuous source, a white light source, through a gas or a dilute solution of the element. And then what will happen is you pass it through a prism, say, or a diffraction grating that light. It'll spread that white light out into a rainbow. But depending upon what the spectrum of the particular gas that the light's been passed through looks like, you'll see these black lines in the spectra, okay? Now the black lines, for example, this is the absorption spectrum for hydrogen. The black lines appear within the rainbow at the same places, same wavelengths, that the bright emission spectra lines appear, okay? So the lines are the same, it's just where do they appear in many cases. And the absorption spectrum consists of those dark lines superimposed on the continuous spectrum of the light source. Now this can be used also to identify unknowns. For example, it's observed often in stars. Stellar spectroscopy is a whole field, and the spectrum of a star can be used to type the star and to figure out what kinds of elements are contained within the star. And it can tell you whether or not the star is an old star or a young star. All right, so this is an example of that. This is the absorption spectrum of our sun. And you can see that they're very complex. And there's tons of little tiny black lines within that continuous rainbow there. And that's because the radiation, the white light from the sun, has to pass through the cooler gases of the solar atmosphere and through the Earth's atmosphere. And there's a lot of different elements in those atmospheres that absorb some of the light that comes out of the sun. But back to the hydrogen spectrum. The first mathematical modeling of the spectrum of hydrogen was done by Johann Balmer and published in 1885. And what he did was he found an empirical equation that correctly predicted the four visible emission lines of hydrogen. And that's the H alpha, H beta, H gamma, and H delta lines, the red, green, blue, and violet lines that we saw in previous slides, at wavelengths of 656, 486, 434, and 410 nanometers, respectively. Now the Rydberg version of that equation is shown here. You can fit that mathematical series to this equation, and that's that 1 over the wavelength of the line is equal to the Rydberg constant times 1 over 2 squared minus 1 over n squared. Here the Rydberg constant is 1.097 times 10 to the 7th inverse meters. And n is an integer that starts at 3 and goes up from there. The spectral lines correspond to different values of n. Now other series were also documented by other gentlemen. The Lyman series is the ultraviolet portion of the hydrogen spectrum, And then within the infrared, you get three different series, the Paschen, the Brackett, and the Pfund. Now they are also fit to a very similar looking equation as the Balmer series. 1 over lambda is equal to the Rydberg constant times, and for the Lyman series, 1 over 1 squared minus 1 over n squared. Now all you do to change where in the continuous spectrum it's located, either it's the infrared, the UV, or the visible, all you do is change that first number within the parenthesis. So the Lyman goes at 1 over 1 squared. The Balmer goes at 1 over 2 squared. The Paschen, 1 over 3 squared. The Brackett, 1 over 4 squared. And the Pfund, 1 over 5 squared. Now the n, you start at one integer higher than your first number. So for example, for Lyman, if you start at 1 over 1 squared with your first number, n has to be greater than or equal to 2. Historically, the formula for the Balmer version of the spectrum was published as the lambda wavelength of each spectral line is equal to lambda limit times n squared over n squared minus n naught squared. Now the limit wavelength was 364.5 nanometers, and n naught started at 2, of course. So this was the first version that Balmer published, and then Rydberg's is the more commonly shown version of the formula now. And what he did was he modified the formula to work for all of the hydrogen series. All you had to do there was change that first number, 1 over 1 squared, 1 over 2 squared, etc. Okay? And so that's the most commonly shown now, and the Rydberg constant was named after him for making that contribution. Now it's important to understand here that they could mathematically model what the wavelengths of the spectrum were, but they couldn't really explain what the physics was that described that spectrum. So this was one of the main failings of classical physics. Like I said earlier, they knew that any successful model of the atom had to describe these spectra, and if it didn't, the model wouldn't work. This was the main evidence they had that explained the structure of the atom. It took Bohr in 1913 to come up with the very first semi-classical, somewhat successful model of the atom, and then of course we now know that that one's not entirely true either. We still use it though because it gives a really satisfying conceptual picture to students. So it's very helpful when you're studying quantum mechanics, for example, to have a picture that you can kind of cling to, even if you know that there's things about it that aren't quite right, because we all know that quantum mechanics is quite difficult for us to visualize. Okay, so our next lecture, we're going to launch into Bohr's model of the atom and talk about its successes and its failures.